Okay, so here we go. Problem one, I'm just going to read this out loud to the group. Hopefully you've had a chance to look at it. But what we have is we have 3 kilograms of water, okay? And 3.0 kilograms of water at 70 degrees Celsius is mixed with 6.0 kilograms of water at 10 degrees Celsius in an isolated system. When the mixture reaches thermal equilibrium, what will the final temperature be? All right, and so notice I said D-gas is back. Yes, I'm sure some of you are loving that. Some of you are not. And remember, D-gas stands for the problem-solving method that I strongly recommend you use. Okay, the D, drawing, the G, givens, the E, the U, unknowns, the E, equation, S is substitute, and S is solve. Okay, all right. So in this case, when we're talking about calorimetry problems, okay, the drawing, I strongly recommend to you, the drawing should be on a phase change diagram drawing. Okay, notice on the right there, I have one put up there. Okay, so we're going to walk through this together. So for the drawing, what I want to do is I want to take these two substances and I want to plot where they are on this phase change diagram. Notice temperature is the y-axis and energy heat is the x-axis. So if I have 3 kilograms of water at 70 degrees Celsius, I'm going to call that M1, and that's going to be like somewhere around right here, where I put that blue dot, M1. Okay, so I have 3 kilograms of water starting at 70 degrees Celsius. Then I mix it with 6 kilograms of water that's at 10 degrees Celsius. So 10 degrees Celsius is going to be lower here, right? This is going to be like right around here. Whoa, no, don't do that. And this would be M2. Make sure I can see this. Okay, so, no, don't do that. There we go, there we go, okay. So my two masses, my two substances that I'm mixing together are basically there and there. Now we know by thermodynamics that what? Mass 1 is going to give up some thermal energy, internal energy we'll say. Some of its internal energy, it's going to transfer to mass 2 in the form of heat. So when these things mix together, when they get to a final sort of equilibrium, it's going to be somewhere in the middle here, marking by this red X, okay? So, and in that process, what's going to happen? I said that mass 1 is going to lose a certain amount of energy. I'm going to call that Q1. And mass 2 is going to gain a certain amount of energy, and I'm going to call that Q2. That was bad. Okay? So Q1 is kind of the amount of energy going from that M1 dot down to the red X, and Q2 is the amount of energy that M2 is receiving from M1 going up, and they're gonna meet somewhere in the middle. Okay? So we have our drawing there, and that's really crucial, right? Because notice what I've set up with my drawing is kind of a conceptual understanding of the problem. And so from there, what are our givens? Well, we know M1 equals 3.00 kilograms. We know the initial temperature of mass 1 is 70.0 degrees Celsius. We know mass 2 is 6.00 kilograms. And we know the temperature initial of the second substance is 10.0 degrees Celsius. Got my drawing, got my givens. What's the unknown? The unknown is what is the final temperature going to be? And notice I can just say one final temperature, right? Because when it says the mixture reaches thermal equilibrium, from the book and the video, I think it was actually the book, thermal equilibrium is when two substances have the same temperature, and therefore they will stop transferring energy between themselves. Okay? So from an equation standpoint, we're at the E in D gas. If you remember, one of the things you should have come across is this idea that in an isolated system, the sum of heat transfers has to add up to what? 0. right? And again, this is a really important point. This is a manifestation of the law of conservation of energy. If a certain amount of heat energy is lost by one substance and the system is isolated, meaning it's not leaving the system, then it has to be gained by the other substances. Otherwise, we would have created or destroyed energy in the process. Okay, so notice this becomes like so. So the Q1 plus the Q2 has to equal 0. Has to. Okay. Okay, so what can we substitute in for Q1? What equation can we use to calculate the amount of heat transfer that was, in this case for M1, the amount of heat energy M1 loses during this process? Well, there's a temperature change, right? And your notes should show you that when there's a temperature change, we're going to use the equation MC delta T, right? So this would be M1 C for the heat capacity of water, delta T1. Similarly, for substance 2, it's also undergoing a temperature change. There's no phase changes in this sort of scenario. So it's going to be a similar equation just applied to it. Its mass times the specific heat capacity of water, liquid water, times its temperature change. And all that has to equal 0. Okay, so delta T1, we can even go further, right? Delta T1, just like, remember, any change of a quantity is what? The final quantity. So this would be the final temperature minus the initial temperature, in this case, the initial temperature for T1. Likewise, we can do the same thing for T2. That would be the final temperature, which again is the same in this case as the T1 final temperature, minus T2's initial temperature. And all that equals 0. Okay, it's going to get mathy here for a little bit, but just hang in there. In fact, actually, let me do a little trick here. This will make it easier. Do you notice? Let me make it a different color. This is going to be so cool. Notice in red here, what do I have? I have C in this term, I have C in this term, right? So what can I do? I can factor that out, right? I can bring that out in front. Let me just do that, because that'll make it easier for us. Go green again. So this is going to be C. And then while I'm doing that, I'm also going to distribute the mass to the temperatures, right? So I'm going to try and get rid of these parentheses. So this could be C times M1 final temperature minus M1 initial temperature of the first substance plus M2 final temperature minus M2 initial temperature of the second substance, end bracket. Let me pause there. I did a couple of math steps there all at once. I just want to make sure. If you aren't quite sure what I did there, if you didn't track it, just, you know, holler, so to speak. Okay, so what can I do then? Notice I can simplify things for myself, because what I can do is I can divide both sides by C. Okay, and then the C goes away. So then what I'm left with, and I'm going to try and do another step here in a second, but notice, let me again use a different color. That goes away. Okay, so and then in this next step, because I don't want to keep writing over and over again, I'm going to take, what are we solving for? We're solving for final temperature, right? So I want all the final temperatures on one side of the equation, and I want everything else on the other side. Okay, so M1 TF is going to be here, and then the M1 T1 is going to, M1 T1I is going to go over here. Notice that when it goes over there, it gets different, the sign on it changes, so to speak. This is M2 final temperature, and this is M2 T2 initial. So notice what I have here is I have that 2 terms on the left, 2 terms on the right. Okay, so again, what I can do here is I want to solve for final temperature. So what I have to do is I have to pull it out so to speak, from each of these terms. So I'm going to do this. Notice what I did there is I just pulled the final temperature out in front, put the rest of the stuff in parentheses, and I get that. Okay, and then finally to solve for final temperature, I just need to divide both sides by this term, the combined masses. And let me, this crosses out. And the final temperature is, whoop, I don't want blue. That was not what I meant. If I get to, whoops, come on. There we go. Final temperature is M1 T1I plus M2 T2I divided by the sum of the masses. An important point I want to make here is I often see students like way back up here at the start of the problem, they start substituting numbers. Oh, I know C is 4186. I know T1I. And notice in this case, the fact that we didn't substitute in numbers really helps us a lot because I got to be honest with you, if you put in those numbers, the number crunching your calculator would get pretty ugly. And yeah, you could do it. And if you did everything right, you get the right answer. But boy, it's a lot more work than just, and it's less elegant than just staying with the letters until you get something that's more simple. And notice what we have here. Some of you may be recognizing this. This is kind of a weighted average. This is kind of the way you do a weighted average in certain circles when you have different terms. So in the end, let's just now substitute numbers and figure out. So M1 is 3. The initial temperature of T1 is 70. And we got M2 is what? 6. And the other one is 10.0. And that's all divided by the masses together, which is 3 plus 6. Okay, when you crunch that out in your calculator, go ahead and take a moment to do that. That's the other thing I would say, really important. Obviously, if you need to use your phone, that's fine. Just I strongly recommend that you don't get in the habit of using your phone because on a quiz or exam, you won't be able to. So I get 270 divided by 9, which comes out to 30.0 degrees Celsius. Always a good idea to go back and say, does this make sense? I had one substance that started out at 10 degrees, the other started out at 70. So the fact that I got 30 is good because the temperature has to be, the final temperature has to be between those two. If I got -3, then I know I did something wrong. And then I just want to give you a sense, some of you may be picking up on this already, but if you're not, that's all right. What I said was a weighted average. And so let's just go back to the problem. And the numbers I gave you in this case are kind of easy. I should say, easy isn't the right word. They lend itself to kind of some proportional reasoning. So notice mass 2 is twice as much as mass 1, right? So mass 2 is 2/3 of the total mass. So wouldn't it make sense that the final temperature would be weighted 2/3 of the way towards its initial temperature? So mass 2's initial temperature was 10 degrees. Mass 1's initial temperature was 70, so the difference there is 60 degrees. So 2/3 of 60 is what? 40 degrees. So what that means is mass 1 should have lost about 40 degrees of temperature because of the whole weighted average thing, right? So 70 minus 40 gives you 30, which is your answer. Okay, so proportional reason is always a good idea to think about, always a good idea to kind of double check your answer. Okay, so let me just pause there for a moment. Let me give students about 20 seconds to do any sort of, if you still have to copy things down, or if you just have had a question that you haven't been able to put it in the chat because you've just been copying down. I want to give you another 20 seconds to do that. If you're good, then go ahead and start looking at problem 2, because that's where we're headed. To be equal to or less than 100 degrees Celsius, justify your answer. And B, when the mixture reaches equilibrium, will the mass of the liquid water in the system be greater than or less than 300 grams? Interesting. You know, what's interesting about this problem is it doesn't ask you for an exact answer. It just asks you, is it going to be above or below a certain threshold? And so let's keep that in mind. Let's use that to our advantage. But first, as always, with dguess, we want to look at the drawing, and this is really important. So again, let us go to the drawing, and in blue here, 10 grams of steam at 100 degrees Celsius. All right, let's just say this is 100, and let's say this is 0 on the scale. Okay, so this is degrees Celsius. So 10 grams of steam at 100 degrees Celsius, where is that going to be plotted on this phase change diagram? Well, it's steam, right? And it's at 100 degrees, so that means M1 is starting out all the way over here, and I want to make special consideration for this, or point this out. I often see students try and put it here, okay? But this is not steam at 100 degrees Celsius. What's this? This spot, let me do a different color. This spot in gray here that I'm about to erase, but I just want to point it out. This spot in gray is water, liquid water at 100 degrees Celsius. So you got to read the question carefully and make sure you're starting the right spot on the diagram. So that M1 is the steam at 100 degrees Celsius. And then the other one is the water at 60 degrees Celsius. And so M2 would be somewhere around here. Okay. All right. So let's look at this. This is interesting. It's a little more complicated, right? Because it looks like we're going to have to deal with a phase change. And in fact, we are. Okay. So what are our givens? Our givens are, what do we have? We have mass 1 is 10.0 grams. By the way, it's also a little more complicated. I'm going to change this right now to kilograms because we need to use kilograms for the reference values, at least the reference values I gave you. So I did a quick conversion there to kilograms divided by 1,000. M2 is 300.0 grams, which is 0.300 kilograms. Okay, what else? We know that T1 is 100 degrees Celsius. We know T2 is 60.0 degrees Celsius, and this is 100.0. Okay. All right. Conceptually, what's going to happen here? Where are these guys going to meet? The question, that's one of the key questions. One of the key questions is the final sort of resting steady state condition of this mixture, where is it going to be? We know it's somewhere going to be between the blue dots, but is it going to be here or here or here? You know, that's basically what this problem is asking you, is figure out where this is going to come out to. Is it going to come out to as all liquid water at some temperature below 100 degrees Celsius, or a mixture of liquid and steam at 100 degrees Celsius? That is kind of the root question, right? So how are we going to figure this out? Well, the first thing we have to figure out is if the mixture will be all liquid or a liquid steam mix. Okay, so to do that, what we need to do is we need to compare the amount of energy released when the steam converts to liquid. I'm not writing very well there. Converts. Okay. So the amount of energy that the steam releases when it converts to liquid. So I'm going to call that QA. Okay. So notice that's represented by that bracket there. What do I have to compare it to? I have to compare it to basically the amount of energy that's required to bring the water up to 100 degrees, because that's what we're figuring out. Is the tipping point, is the final steady state point to the right of this, or basically, is it going to be 100 degrees, or is it going to be less than 100 degrees? So compare the amount of energy, boy, I wrote really badly there. Sorry about that. Released when steam converts to liquid, which I'm going to call QA, to the energy required to get liquid, to 100 degrees Celsius, and that's QB. okay? And in fact, I want to be a little more exact. I'm looking at absolute values here, okay? Amount of energy, because in this case, what's going to happen? The amount of energy that QA gives up goes into QB, all right? And so if we discover that QA is greater than QB, then what does that mean? Then the liquid is all going to get to 100 degrees Celsius, and we'll have a steam water mix at 100 degrees Celsius. If we discover that QB, the amount of energy that the liquid needs to get to 100 degrees, is more than QA, then we know that what's going to happen is QA, the steam is going to keep losing energy, and then some of it's going to convert to liquid. Does that make sense? Okay, so how do we figure out QA? Well, notice QA is a phase change. So QA, we have to use the phase change equation, which is the mass of M1 times the latent heat. Now, there's two latent heats that we talked about, or that the book and the videos talk about. And this is latent heat of vaporization, because we're talking about vapor, right? Steam to liquid. The other one is latent heat of fusion, which has to do with solid to liquid. Okay, so M1 LV. So M1 is 0.0100 kilograms. And the latent heat of vaporization you're going to get from the reference value there, which is, what did I give to you guys? Because I have something different here. Is it 2.36 times 10 to the 6th, I think? I'm going to call it that. If it's not, someone tell me. Okay, so let's go ahead and calculate that. 0.01 times 2.36, 10 to the 6. What do we get? 23,600 joules. Okay, so that's QA. So that's how much energy the steam can give up and still be at 100 degrees. Basically, as it gives it up, it's going to turn into water, but it'll be a steam-water mixture. Or if it gets all the way to 23,600, it'll be all water. So let's compare that to QB. QB is going to be mass 2 C times the change in temperature for it to get to 100 degrees. Right? Because we are at that other spot in the phase change diagram. Okay, so mass 2 is 0.300 kilograms. The C is 4186 joules per kilogram degrees Celsius. That's that reference value from that table. And the delta T is, the final would be 100, and the initial is 60. Do that in your calculator. 0.3 times 4186 times 40. QB is 50,232 joules is what I get. Please feel free to double check me. Don't take my word for it. Okay. So what does that mean? So the absolute value of QB is greater than the absolute value of QA. In other words, it requires more energy to raise the water from 60 degrees to 100 degrees than the steam can give up. The steam is going to be all liquid water, and it's going to start cooling down before all of the M1 water all the mass 2 water has reached 100 degrees. So because of that, the final temp will be less than 100 degrees Celsius. Okay, again, let me pause there for a second. Give people a chance to kind of write that down, absorb it, ask any questions. By the way, we're going to get a break here soon. So if you're just kind of hoping for a break, you're going to get one here in a moment. Because this is the answer to part A, basically. If you're looking for the answer, this is the answer to part A. All right. Part B, let's go back. What does part B say? Part B says, what will the final mass of the liquid water be? Will it be 300 grams or more than 300 grams? Well, if you think about it, we learned from part A that the steam is going to get all the way to be liquid water, and then it's going to keep cooling down, right? So in other words, all the liquid water you had, the 300 grams you had, none of that's converting to steam because it doesn't get to 100 degrees. And in fact, some of the steam, in fact, all of the steam gets converted to liquid water. So what we can say, whoa, that was bad. What just happened here? Resume share. Okay, good. Woo! I don't know what happened there. That was weird. Okay, so what we can say is all steam will be converted to liquid water. So final mass of liquid H2O greater than 300.0 grams. Okay. David, I see the questions going back and forth. The one thing I would add just to maybe make you aware of this, we could have written, it would have been totally legitimate. David's asking a question, why, I think the question, if I'm interpreting it correctly, is why didn't we go this route and say sum of q's equals 0? We could have done that, okay? We could have done that. That actually makes this problem even more complicated because then what I have to do is I have to basically, and actually you're gonna have to do this for lab next week, by the way, so we're getting there. But in this case, I have 3 heat transfer terms. If I do that, now that I know, let me go back here. Actually, no, I'll draw it down here. So if we wanted to go this route, by the way, this is extra, and I'm kind of trying to explain why I didn't do this, but one mass started here, one mass started here, okay? We know now that the final mixture ends up here. So in this case, this was QA. Now we have Q, I'm gonna call it QC to differentiate it, and we have QD. Okay, so I could have written, now that I know this, that it ends up around here, I could have written that QA plus QC plus QD equals 0. And I could have done all the substitution, and I would get something that looks a little uglier math-wise, but I could solve it. And in fact, you're gonna have to do that next week for a slightly different scenario, but with similar ideas. Okay, so I hope that helps. Okay, so what I'd like to do now is, let me do this. Let me leave this up here because I suspect some of you might wanna still look at it. So let's go and take a 3-minute break because what's gonna happen is when the